In this video, we will be looking at homogeneity of physical equations. Now, what exactly does it mean for an equation to be homogeneous, right? An equation is said to be homogeneous if each term in the equation has identical base units. So an equation is said to be homogeneous if each term in the equation has identical base units. So the first question that may automatically come to mind is, how do we identify the terms in an equation? Now, in an equation, basically, each term is a single variable or group of variables separated by a plus sign, a minus sign, or an equal sign, right? So each term is a single variable or a group of variables separated by a plus sign, a minus sign, or an equal sign. Now, let's look at a few equations and we will determine exactly how many variables or how many terms rather are in those equations. The first equation to look at is one of the equations of motion, V equals U plus AT. Now, how many terms are in this equation? Now, if you look at our definition or our explanation of what a term is, we said each term is a single variable or a group of variables separated by a plus sign, a minus sign, or an equal sign. So if we look at this equation, we see that V and U are separated by an equal sign, and U and AT are separated by a plus sign. And so therefore we have 3 terms in this equation. So V is a term, U is a term, and the combination of A and T together gives us the third term. Let's look at another equation. S equals UT plus a half AT squared. Now, how many terms are in that equation? We have S, we have UT, and a half AT squared. Again, that equation has 2 terms. Now let's look at another equation. Suppose we write this one. V equals S over T. Now there's only one sign in this equation, which is an equal sign, and it means that we have 2 terms, right? So typically the number of terms is 1 greater than the number of signs in the equation. What exactly does this mean? In the last equation we wrote, V equals S over T, there's only one sign, a plus sign. 1 plus 1 is 2. We have 2 terms, V and S over T. In the second equation, there are 2 signs, an equal sign and a plus sign. So 1 plus 2 is 3. That gives us 3 terms, S, UT, and a half AT squared. Similarly, in the first equation, there are 2 signs, a plus sign and a plus sign and an equal sign. So 2 plus 1 gives us 3. So therefore there are 3 terms, V, U, and AT. So the first part of being able to check if an equation is homogeneous is to be able to determine exactly how many terms are in the equation, right? Now once that is done, what we will do is to break down or to express each term in terms of its base unit equivalence and then determine whether the equation is homogeneous or not. So since we have these equations, let's check if they're homogeneous. Let's start with the first. V equals u plus at. So we can basically draw up a little table, perhaps. So we can start with the term, and we have the base unit, right? So the first term is v, which represents velocity. Now, what is the SI unit of velocity? The SI unit of velocity is a meter per second, and those are already expressed in base units, so we'll write it down, meter per second. U also represents velocity, but initial velocity, and therefore has the same units as v. Now, at is not a single variable, but two variables, a and t, being multiplied together. And so therefore, to get the base units of at, we must multiply the base units of a by the base unit of t. So for at, the base unit would be the base unit of a, which represents acceleration, of course, whose units are the meter, or is the meter per second squared. Time, SI unit of time is the second. And so when you multiply meter per second squared by the second, we realize that there's an s to the minus 2 and an s, which brings us back to the laws of indices. According to the laws of indices, when multiplying indices with the same base, we keep the base and we add the powers. So this gives us m s to the minus 2 plus 1, which gives us meter per second. Now, having expressed each of these terms in their respective base units, we will then compare the base units and determine whether the equation is homogeneous or not. So meter per second, meter per second, meter per second, and therefore this tells us that, or this shows us rather, that the base units are identical, and therefore the equation is indeed homogeneous, right? But of course, we know the equation to be correct. This is the correct form of the equation v equals u plus at, one of the equations of motion. And because the equation is correct, we expected it to be homogeneous, right? Now, let's check the second equation for homogeneity. So, we started by writing down the equation. So, we have S equals ut plus a half at squared. So, similar to the first equation, this equation also has three terms. So we begin by identifying the terms and then expressing each term in terms of its base unit equivalent. So we could put the term, and on the other side, put the base unit. So the first term is S. Now S represents displacement, or sometimes you may say distance. Sometimes the words distance and displacement are used interchangeably, even though they're not exactly the same things, right? So S represents displacement. What is the SI unit of displacement? The SI unit of displacement is the meter, symbol m. The next term in the equation is ut. Now u represents initial velocity, and t represents time. And so ut will have base units, meter per second, representing u, and we multiply that by the second representing t. When we combine those two, again, back to the laws of indices, when multiplying indices of the same base, we keep the base and we add the powers. So s to the minus 1, and this s, of course, is the same thing as s to the 1. So when we add those two, or when we combine those two rather, we get meter s to the minus 1 plus 1, which of course, same thing as meter s to the 0. And from the laws of indices, any base raised to the power of 0 just gives us 1. So this of course is equivalent to the meter, right? Lastly, we examine the third term, a half at squared. Now, half is just a number. It has no units whatsoever. It is just a multiplying constant, and therefore it will not affect the base unit of this term, right? So the unit of A, acceleration, is the meter per second squared. Now t represents time, unit of which is the second. But because it is t squared, then the unit of t squared, of course, is the second squared. And of course, when we combine these two, minus 2 plus 2 gives us 0. Again, we're applying the laws of indices. And so this gives us meter s to the minus 2 plus 2, which is meter s to the 0, which is simply meter. So having expressed each of these terms in their respective base units, this is the meter, meter, meter once more. So the three base units are identical, and therefore the equation is homogeneous. Again, this equation was indeed correct. It is another of the equations of motion, and we know it to be correct. So basically, we expected it to be homogeneous. So essentially, if the equation is correct, it will be homogeneous. But does the reverse apply? If the equation is homogeneous, does it automatically mean it is correct? We will use the next example to demonstrate or to answer that question. Now, let's look at this equation. V squared equals u squared plus as. Now, let's pretend that we've never seen this equation before, so we don't know if it's correct or not. All right? Let's just pretend, because, of course, it is an equation that we ought to be familiar with. So let's just pretend that we've never seen this equation before, so we cannot tell if it is correct or not. We will check this equation for homogeneity. So again, we start by identifying the terms in the equation. And there are three terms: v squared, u squared, and as. So we'll draw up a little table for the terms. So for the term and for the respective base units. All right? So the first term is v squared. Now v, again, represents velocity, and the SI unit of velocity is the meter per second. So therefore, because v is being squared, means that we must also square the units of velocity. So the base units of v squared would be meter per second, and we square all of that. Now, again, from the laws of indices, when you square an index, you basically multiply the powers. So this meter would essentially be meter to the power of 1. So when you square this, you now get meter. So the 1 times 2, that gives us meter squared. And then s to the minus 1 times 2, that is s to the power of minus 2. So the base unit of v squared would be meter squared per second squared. Right? Now let's check the second term, u squared. Now u, as we mentioned before, represents initial velocity, and therefore it will have the same units as v. So same thing, meter per second, and we square all of that, and that will give us meter squared per second squared. So far, our two terms have identical base units, but that is not sufficient to determine whether the equation is homogeneous or not. We have to proceed to express a third in terms of its base units, and only then we will be able to determine whether the equation is homogeneous or not. So we proceed with the term as. Again, u represents acceleration. The SI unit, or the base unit of what, is a meter per second squared, ms to the power of minus 2. S represents distance or displacement, and the unit of which is a meter. So we're going to multiply by the meter. So here we have meter times meter, which gives us meter squared. And so this gives us meter squared per second squared. Now, having expressed each term in terms of their respective base units, we'll compare them. So we have meter per second squared, meter per second squared, meter per second squared, And so what we observe is that each term has identical base units, and therefore the equation is indeed homogeneous. But is the equation correct? Now, earlier we said that we should pretend like we've never seen the equation before. But of course, we know what the equation is supposed to be. The correct form of the equation is v squared equals u squared plus 2as. So, what have we noticed from this example? We've noticed that basically, by simply omitting the number 2 and multiplying constant, the equation being homogeneous is not affected. So what does this mean? It basically means that the absence of some multiplying constant, right, like a numerical factor like 2, a half, or so on, will not affect the equation being homogeneous or not. And basically that is one drawback of using the method of homogeneity to check an equation, right? If a certain number or just a multiplying factor is missing, then the method will not reveal it, because it will still show that the equation is homogeneous if all that is wrong about the equation is the omission or even the presence of a numerical factor which is not supposed to be there. So that is one drawback of using the method of homogeneity to analyze equations, right? The omission or even the presence of some numerical factor will not affect its homogeneity. Now, what we will do next is to use an example to demonstrate another limitation of this method of checking equations for homogeneity. And what we will do is we will deliberately use an equation which we know to be wrong, right? So, for instance, let's look at another equation. Suppose we have this equation S equals a half AT cubed, right? I mean, we should be able to tell what is wrong with that equation, of course, because there is an equation which it is somewhat related to. But again, let's pretend that we've never seen this equation before, and so we cannot tell whether it's wrong or right. Let's pretend. But of course, the symbols have their regular meanings. So S represents displacement, A is acceleration, and T represents time. So we look at the terms, and of course, we express each in terms of their base units. So S represents displacement, the base unit of which is the meter, m. Half AT cubed is the second term in the equation. Again, as we mentioned before, the number half is just a multiplying constant and obviously has no units and will not affect whether the equation is homogeneous or not. And so therefore, in terms of the base units, we have the units of acceleration, which is a meter per second squared. We have the units of t cubed. Now t represents time, the SI unit of which is the second, and so therefore t cubed will have units s cubed. Now when we combine these laws of indices again, we keep the base s and we add the powers. So this gives us meter s to the power of minus 2 plus 3, which is equal to meter second. Now if we compare the base units, we have meter second and we have meter. And clearly, those two are not identical, and it therefore tells us that the equation is not homogeneous, right? So what does this mean? What logical conclusion can we draw when the equation is not homogeneous? Now, provided that we did not make an an error or a mistake somewhere, which of course we did not in this question, then if the equation is not homogeneous, we can categorically state that the equation is incorrect. So therefore this equation is not homogeneous, which therefore means that this is basically an incorrect equation, right? But if the equation is incorrect, obviously it means that there's an error somewhere. Does this method reveal where the error lies? It doesn't, right? Now earlier we said that we should pretend that we've never seen any equation remotely resembling this one before. So if we had never seen an equation looking like this before, we would not be able to tell exactly where the error occurred. But because this is an equation with which we have some familiarity, the correct form of the equation is actually equation 2 that we looked at earlier, which is S equals ut plus a half at squared, right? So because we know this equation from before, we can identify exactly where the error occurred. And as a matter of fact, there were 2 errors in the equation, but however, only one error resulted in the equation not being homogeneous, right? If we compare this to this. So the first error is that the term ut was missing. Homogeneity does not detect that any at all, because if we had written a half at squared, the equation would have been homogeneous. So that method does not reveal any missing term in the equation, right? However, the error that was picked up, or which eventually revealed itself, or maybe not itself, but the error which led to the equation not being homogeneous is the power 3, which should have been 2, right? So basically we've used these examples to check if equations are homogeneous, and by doing them we've basically showed that there are a couple flaws in using the method, and we'll basically just jot those down, right? So these are the drawbacks of using the method of homogeneity. The equation may still be homogeneous if a numerical constant or a numerical factor is missing. So is missing, or we could say wrongly introduced. Right? So basically this means is that if we were to simply remove the half from this equation, it would still be homogeneous. So the method does not reveal any inaccuracies in the numerical factors or multiplying constants, right? Which is just another way of phrasing this shortcoming, right? So the equation may still be homogeneous if a numerical factor is missing or wrongly introduced. Or in other words, this method does not reveal any inaccuracy or missing numerical factor or constant, right? 2, if the equation is not homogeneous, if the equation is not homogeneous, unless we know the correct form of the equation, unless we know the correct form of the equation, we won't be able to tell where exactly the error occurred. right? And these basically are the drawbacks, or two of the drawbacks of using this method of homogeneity, right? So we said that basically if the equation is not homogeneous, provided we did everything correctly and we did not make a mistake, then it therefore means that the equation is incorrect. But unless it is an equation, with which we are very familiar, we will not be able to tell where the error occurred. Now, this mention of this example also could reveal a third drawback. The equation being homogeneous does not reveal any missing term. As we said before, if we were to remove ut or even remove a half at squared, the equation would still be homogeneous despite term being missing, right? So again, the equation could still be homogeneous if a term is missing. So not only will a missing numerical factor or multiplying constants not affect the equation's homogeneity, a missing term may also not affect its homogeneity, and therefore that is another drawback of using this method of homogeneity. So in this video, just to recap, we looked at the homogeneity of physical equations. We spoke about what it means for an equation to be homogeneous. We looked at examples of checking equations for homogeneity, and we also looked at the drawbacks of using the method of homogeneity to check equations.